Hey juniors, how's it going? So hopefully you get a chance to at least flip through the pages of the lever assignment that I was talking about, first, second, and third class levers. What's following is a short lesson on what they are and what I expect you to know about them. And we're going to be moving on from there. I'm going to try and figure a few things out, like I mentioned before, give you a SolidWorks assignment that you can work on in addition to some of the book work. Because if we do nothing but book work over the next month, no one's going to like it, and probably only half the people are going to do it. But anyway, so hang in there, and I'll be getting some stuff out to you. Don't forget to check the office hours. It's a chat room, so you'll be able to get in, no problem, and ask away any questions, okay? Or you can email me directly if you want. See ya. All right, folks. Rather than using some fancy green screen video tricks, I'm going to go old school, and I'm basically recording something that I'm writing down. I'll get better, and I might even record myself as I'm doing stuff on the board, but for the time being, this is going to have to do. So we talked about first, second, and third class levers, or levers. I don't care what you call them. Levers, levers, potato, potato. And there's three classes. And this is what I want you to make sure you understand. What does each one look like? How do they differ? So that if I ask you, draw me a first, second, and third class lever, you can do that. Or at the very least, identify them. Right? I'm not going to try and trick you. At least not yet, anyway. So, if you have a fulcrum, and here's your lever. Our first class lever is going to be one in which you have your load here and your effort here, and this is the fulcrum. Fulcrum is the point of rotation, if you want to call it that. This is pretty common when you have a seesaw and you have a person on either side. You're trying to lift one or push the other one. Pretty straightforward because we see that all the time, right? So that's a first class lever. It doesn't matter whether the load and the effort are on the left or on the right, but they are on opposite sides of the fulcrum. Now when you go to the second class lever, you have the load here and you have the effort here. So notice that you'll have the load now is in between the effort and the fulcrum. Whereas on this side you had one on either side, and here we have the effort all the way on the outside. Why would you use such a thing? Well, if you think about a wheelbarrow, for example, and you're standing here and you're going to be lifting a bunch of rocks, this is what your load is, and it just so happens that you put a wheel on it. Somebody a long time ago thought that adding a wheel to this would be a good idea, and sure enough it was. And you have your effort here. You're lifting and you're able to overcome that load. So that's the second class lever. So now the third class lever is very similar. You have your fulcrum here, except that now you have the effort here and the load here. So notice the difference. And you might think, well, if I'm standing here and I'm pushing on this, it seems like it's not going to go anywhere. It looks like it's a lot harder and not very efficient. Third class levers are not used as much because it is in many cases is of mechanical disadvantage. And if we talked about this before, if you want to work harder instead of easier, you go to the gym. So a lot of the weight machines and exercise equipment out there is based on a third class lever in which the load is going to be on this side. So just know that the difference between the three, you have load and effort on opposite sides, and this one you have effort with load in the middle and fulcrum on the outside, and number three where you have effort in the middle and load on the outside. So those are the three that you are going to be responsible for knowing. We are then going to move on to how do we calculate things? How long does the lever have to be in order to lift something, etc., etc. But right now the main thing you have to learn is what kind of levers do we have and how to identify them. So now we're going to talk about how do we use these to our advantage and how do we calculate certain things. Well, the whole title of our chapter that we first started on was Mechanical Advantage. How do we use simple machines to make our jobs easier, to make the world an easier place to live in, and to do things we can't do or too lazy to do, make it easier on ourselves. I'm going to draw again our first class lever. Now, what I'm about to say applies to any lever, but in this particular case, I'm just going to draw a first class lever. So what's going to happen is we're going to have a certain distance. The distance here, we're going to call it RL because this is the load, and the distance here, we're going to call it RE because this is the effort. And once again, this is the fulcrum in here. And this is something you're going to want to write down, or at least remember. The ideal mechanical advantage of any lever is the ratio between the radius of the effort arm and the radius of the load arm. What the hell does that mean? So, ideal mechanical advantage of a lever is equal to the radius of the effort arm, which is this guy here. Now, by radius, it just means the distance. It is called radius because if you were in space and you push on one, everything will kind of rotate around the fulcrum. But in our real world, that's not going to happen. So you have the radius of the effort arm over the radius of the load arm. That is going to be the equation that we're going to be using for the ideal mechanical advantage of any lever. Now, what about AMA, actual mechanical advantage? Well, that one we don't know until we actually test it. So ideal versus actual, we have to test it. If you tell me that the ideal mechanical advantage of a particular lever setup is 2-to-1, but when I go to try and lift equipment or rocks or whatever, and it turns out that it's not 2-to-1, then it makes it a little bit different. This particular example is one that was from the book, but I'm going to kind of walk you through it, make sure that we understand what's going on. We are given a lever and a fulcrum, and this is a second class lever because we have the load in the middle, the effort on the outside. They give us that the distance between the effort and the fulcrum is 8 feet, and the distance between the load and the fulcrum is 4 feet. So let's find out, first of all, what is the ideal mechanical advantage of the lever? So IMA, we said earlier that it is the radius of the effort over the radius of the load, or the distance between the effort force and the fulcrum, and the distance between the load and the fulcrum. So in this particular case, they gave it to us. They didn't want us to figure it out necessarily. So one of them is 8 feet, and the other one is 4 feet. So we see from here that it is pretty darn simple. The ideal mechanical advantage of this second class lever is 2. Okay, cool. Now, they tell us that this is a 90% efficient lever. So if 90% efficient, so that means that we really have 10% that is lost, and we'll come back to that. So the next question is, what is the ideal effort force that would be needed to move the lever in the absence of friction? So without any friction, what is going to be our ideal effort force? So the ideal effort force, we said that this thing weighs 150 pounds, but because we are using a lever, it's going to weigh less. And why is it going to be less? Well, in this case, we have a mechanical advantage of 2-to-1, which we just saw in here. It turns out that this particular mechanical advantage is 2, so our effort is going to feel like 75 pounds. All right, so hopefully that makes sense. We divide basically the load by the ideal mechanical advantage. That's what's going to be our actual effort force. But we know that it is not a really efficient. It's not 100% efficient, right? So what is the mechanical advantage or the efficiency and so on? So AMA, is it going to be less than or greater than the ideal mechanical advantage? Well, it's going to be less than the ideal mechanical advantage because that's what life is. We have losses due to friction and so on. In this particular case, we said that it is 90% efficient, so AMA is going to be 0.9 for 90% times 2, which is 1.8. So our ideal mechanical advantage was 2, but our actual mechanical advantage is 1.8 because it is only 90% of that. So when we go ahead and figure that out, what's going to be our actual mechanical advantage, or how much is it going to feel like? Well, our load is still going to be 150 pounds, but this time our mechanical advantage is not going to be 2 like it was up here. It is going to be 1.8, which means this is going to feel like 83.3 pounds. So once again, we have a second class lever with a load of 150 pounds. Second class because the load is in between the effort and the fulcrum. This particular equation is going to be the same regardless of whether you have first, second, or third class lever. We have the radius of the effort divided by the radius of the load, and it gives us an ideal mechanical advantage of 2. If everything were perfect, we divide 150 pounds by 2, and it would feel like it is 75 pounds. But in real life, everything's not perfect, so the actual mechanical advantage, which is going to be less than the ideal mechanical advantage, they already told us that this thing is 90% efficient. So we take 90%, or 0.9, and multiply it times our IMA. That means it is really 1.8 in real life. So the 150 pounds is not going to feel like 75. It's going to feel like a little bit more. So we divide it by 1.8 and we get 83.3 pounds. So you should be able to take one of these. I'll give you certain numbers and calculate it out. Okay?